Good morning, everyone. I'm Shine Kim from Seoul National University and Samsung Electronics. Today, I'm going to talk about Behemoth, flash memory-centric training accelerator for extreme scale DNNs. This is a joint work with my colleagues at Seoul National University and my advisor, Jae Lee. The deep neural network have become widespread in various application domains. There has been continuing effort to further improve model accuracy, and scaling the model size is one of the most popular ways to achieve this. The figure shows that the size of an NLP model has increased by more than 1,000 times over the last 2 years. Before going deeper into my work, I would like to briefly talk about the DNN training process. It is a repetitive process of matrix multiplication between activation, weight, and gradient matrices. The DNN training process can be split into 3 steps. Step 1 is forward pass, where activation and weight matrices are multiplied to generate unexpected value. The activations are created in this step are stored for later use. And then the expected value is compared with the ground truth to calculate the error or loss. During the backward pass, the loss is propagated and gradients are calculated, which are used to update the weight. In doing so, both stored activation and weight are used. In this work, we aim to break the memory capacity wall in extreme scale DNN model training. This problem is caused by the huge size of DNN models. Therefore, the model parallel training, which distributes to a single model through multiple GPU, has become the de facto standard. For example, GPT-3 consumes 700 GB of memory just for weight, and thus at least 18 GPUs with 14 GB RAM are required to hold this model. However, the model parallelism has inherent drawbacks, such as load imbalance among partitioned models due to non-uniform layer sizes. Furthermore, according to our analysis, we have found that such extreme scale models often cause lower utilization of memory bandwidth. This underutilization is caused by a much higher degree of data reuse due to an increase in matrix size. Continuing with the previous example, GPT-3 requires 15 GB per second bandwidth when training with batch size of 16 on 840 teraflops compute core, while GPUs support in total of 28 TB per second throughput. Consequently, a significant memory bandwidth underutilization occurs. Therefore, scaling of DNN necessitates a new memory system with large capacity and low cost. We must hold the entire DNN model in a single node to enable data parallel training. Behemoth platform is composed of several nodes that have the same hardware components. Each node has compute core for matrix computation, tensor buffer to give tensor using DDR-DRAM, and NAND flash memory to store tensors. Especially, Behemoth adopts a novel two-level memory architecture using a DDR-DRAM and NAND flash memories to reduce the cost of DNN training. That's the principal difference between Behemoth and conventional training system that use the HBM as a single-level memory system. Behemoth platform consists of multiple activation nodes and a single weight node, enabling data parallel training. The activation nodes store activation and perform matrix multiplication using activation and weight, whereas weight node serves as a parameter server to aggregate gradient from individual activation nodes and update weight. The host system transfers a command sequence to Behemoth via PCIe interface, and the Behemoth trains the model according to the command sequence and returns the training result to the host. Let's move on what's happening inside Behemoth after receiving command sequence from the host. DNN training is a repetitive process of forward and backward propagation. At the start of forward propagation, weight node reads weight from NAND flash to its tensor buffer. Then the weights are broadcasted to the activation nodes. In step 3, weights are loaded into SRAM of their compute cores, and then compute cores perform matrix multiplication using those weights. After computation, the activations are stored back to their tensor buffer, which are finally returned to the NAND flash memory. And backward propagation proceeds in a similar way of forward propagation. However, in this process, naively replacing the HBM memory system to a conventional SSD fails to satisfy the memory bandwidth requirement for DNN training, so we propose flash-based memory system, or FMS, specialized for extreme-scale DNN training. To train extreme-scale DNN without performance degradation, FMS should provide at least several tens of gigabyte second bandwidth. Furthermore, FMS has to guarantee at least 5 years of endurance. First, I will explain how we can scale FMS bandwidth to several tens of gigabytes per second. Although modern SSDs use many NAND chips to increase their throughput, a single SSD fails to provide several tens of gigabytes per second bandwidth because the SSD firmware is becoming a new performance bottleneck. So, to overcome the firmware bottleneck, hardware automated data paths can be a solution. However, the complex function of FTL make it difficult to adopt a specialized hardware-based data paths such as garbage collection, wearabeling, and persistency support. Therefore, we've simplified FTL function by adopting multi-stream feature and making write sequential. FMS supports 3 different streams according to data type for DNN training. Notably, we focus on managing volatile stream or V streams, which store intermediate tensors generated during training iteration, like activations. Furthermore, as shown in the figure, FMS only allows strict append-only sequential rate so that the FTL is very lightweight, and this DC function can be removed and wearabeling function can be replaced by a simple round-robin flag allocator. As a result, the V-stream is fully managed by hardware logic, and this FMS can sustain over 15 GB per second throughput by removing the firmware bottleneck. From now on, I'm going to talk about how to improve the endurance of FMS for training. Basically, the endurance of a NAND flash-based storage relies on the program and erase cycle for NAND blocks. Unfortunately, because Behemoth utilized NAND flash memories as a temporary buffer for the training data, the NANDs are frequently programmed and erased. So, to increase maximum P cycle of FMS, we trade retention time for higher P cycle and maintain very low WAP, nearly 1, via sequential rate. First, as shown in the figure, the lifespan of those intermediate tensor is less than 1 minute at maximum. We can reduce the data retention requirement from 1 year to several days. This reduced retention time requirement can increase the maximum number of P cycle without any additional hardware resources. Moreover, as shown in the right figure, Behemoth generates only sequential write during the training iteration to feature a very low write amplification factor, nearly 1 in this case. We evaluated our platform's effectiveness by comparing our platform's memory cost to TPU-based DNN training system and comparing the training throughput of Behemoth to the conventional SSDs. To model Behemoth, we integrate two simulators, Maestro for compute core and MQCM for FMS. We evaluated our platform with two types of model, BERT GPT-3-like and T5-like, and we scale the dimension of attention layer by up to 4 times to model future DNNs. Here are memory cost evaluation results. We set the hardware parameter to finish training with 10 days, as listed in the table. As shown in the figure, the memory system of TPUs are 3.65 times more expensive than the memory system of Behemoth. The next evaluation is to compare training throughput between FMS and conventional SSDs. A 2 TB FMS and 500 GB conventional SSD are compared. Here is the evaluation result for training throughput. Behemoth is close to the ideal case where there is zero overhead from memory system accesses, whereas Behemoth core with 4 conventional SSDs shows much lower training throughput compared to Behemoth with FMS. And the firmware bottleneck of conventional SSD is a major cause of performance degradation. To summarize, Behemoth enables effective data parallel training of extreme scale DNN model, and Behemoth shows 3.65 times memory cost saving over TPU v3 and 2 times training throughput improvement over commercial SSDs. This is the end of my talk. Thank you for listening, and please refer our paper for more detail.